Much of the power of artificial intelligence comes from copying natural mechanics of the brain. Neural networks learn by reshaping connections between artificial neurons across multiple layers based on the outer layers of the brain, the cerebral cortex. These layers seem to be where much of our knowledge and memory live. When the brain is studied, scientists try to figure out which parts of the cortex are activated for certain kinds of thinking. It still isn't well understood what is exactly happening in those layers and how it really learns. It is nearly impossible to watch and analyze what's happening in millions and billions of living neurons, but it is possible in artificial ones. Neural networks in AI are set up with an input layer, an output layer, and various hidden layers in between. The input takes the raw set of data that the hidden layers use to extract meaningful features and identify or manipulate them in the output layer. As it gets exposed to more and more training data, each layer gets better at doing its job, making fewer and fewer mistakes. By reducing the error, it is said to be able to fit the data better. This fitness is what gives AI its abilities. A tight kind of fitness ends up creating what we consider memorization. It overfits the data, meaning it matches very closely to what it trained on. This makes it good at recognizing those specific examples, but bad at generalizing to new ones it wasn't trained on. When it is more loosely fitted, it gives up some detail and accuracy through abstraction to gain more general intelligence, able to flex and adapt to different cases. The best AI is able to balance these two properties to be as accurate as possible while still being able to generalize. A part of these opposing forces comes from the width and depth of the neural layers. A neural network that is very wide, with very few layers, is able to memorize well. Having many neurons in a single layer allows each one to remember exact details. Each neuron could represent your preference for a restaurant. With enough of them, it can remember every preference for every restaurant you've ever rated. If we have less width and many layers, it does something unusual. It learns to abstract the data by extracting meaningful features. Each layer learns which details are important to pass on to the next one, like a game of telephone. As features are detected and passed on, it becomes less and less like the original data. It becomes more abstract. When detecting faces in pictures, the layers are able to represent lines and shapes, then parts of a face, eyes, noses, mouths, which eventually make up faces of people you know or expressions you recognize. Vision, through the brain's visual cortex, has been found to do the same thing, picking out one feature at a time. Our brains likely use the same computational process as neural AIs. As we learn and experience things, the neurons in our brain are constantly rewiring themselves from layer to layer, from region to region. It is following a neural algorithm that evolved to learn automatically. The competition between wide memorization and deep generalization in AI could also be present within the cortex. This could explain how humans and other animals are able to learn. It could also explain why different people learn and behave the way they do. Some abilities require a great deal of precision, recalling very exact and very specific details. Math and coding follow very strict and unbending rules of logic. Science and engineering jobs usually need to use precise tools and methods and follow specific designs with very little room for error. Building a space shuttle is very precise and hard to generalize. However, generalization is essential for working with people. Each of us comes from vastly different backgrounds, raised in different families, have different bodies and different brains. We all dress, move, act, think, and feel differently. Even when we share a language, we each speak our own way, using certain words, tones, pacing, and with our own voice that sounds like no one else. What one person says may mean something entirely different if said by another, and sometimes we don't say what we mean at all. We have to be flexible in order to understand one another. This may explain some of the diversity in thinking styles we could be born with. Each gender tends to prefer certain kinds of jobs. Women are drawn towards people-oriented positions like teaching, administration, and nursing, while men towards technical and physical work like construction and the trades. This trend shows up even in nations that actively promote social equality like the Netherlands. If we go to the extremes of the strict memorization style of thinking, it resembles the characteristics of autism. Autistic people usually like controlled environments and repetitive behaviors. Some have incredibly precise memory, able to play any music by ear or possess photographic memory. They also tend to have trouble reading social cues or facial expressions and take things very literally. On the other hand, extreme generalization can be found through hyperempathy. People with Williams syndrome can be very social and sense others' feelings very easily, yet they have trouble learning to read or focus their attention. Whether these wide or deep models of neural networks apply to brains and their thinking styles has yet to be confirmed. However, the continual advancement in AI is able to shed some light on the understanding of psychology. As neuroscience gets better at mapping live neurons in brains, it will further bridge into computer science, giving rise to a greater understanding of our natural intelligence. One day, we may be able to measure and explain the style of thinking in all kinds of brains, and how each one learns to understand the world around them.